This is another clip about how you can do some good lesson planning by feeding Python a good math topic. It's a good way to develop your Python skills and to learn math at the same time. So you have your favorite math books out, and one of mine is the Book of Numbers by John Conway and Richard Guy. Highly recommend this as a goldmine of topics. And almost at random, you can just pick any topic. I'm going to look at perfect numbers in connection with the Mersenne primes as they're linked in Euclid. Although he didn't use that vocabulary, it's part of the brilliance of this book, Numbers, that we can use contemporary vocabulary and now a computer language. Hopefully still contemporary when you look at this. So it's a dual topic here. I'm taking a list of generating primes. These are what you feed to a generator, and Python generator expressions could be your focus in this, and as far as having a Python topic. Use curly parentheses, not square brackets, but otherwise use list comprehension concept. So I think Alex Martelli might be responsible for this nifty feature. In any case, it's one of the tools we're going to need to investigate this Euclidean proposition. Um, there was a corner case my previous little divisors algorithm wasn't handling properly when I fed it a perfect square. It gave back the same divisor twice. So I decided to redo this video, and here I am in the math teach list, where for so long I've been pushing this idea that we should be liberating kids from calculators and giving them something more interesting to study math with. In other words, computer languages. And Math Teach is where you can read Pam and Shelley, great writers there, and it's a wonderful list. It gets kind of cantankerous, but math teachers are entitled to their passions, aren't they? Math wars. It's pretty. We throw food a lot. So back to Python. What I'm going to do to help teach generators is test Euclid's proposition, not proving it here. I'm just sort of running a test to see if it's making any sense, what he's claiming. And I'm going to go through these Mersennes, but I only lazy evaluate. It's on demand. It's when I ask for the next one, I get the next one. And you're going to see that's important. So I'm raising 2 to a huge power, well actually not that huge a power, and subtracting 1. As p jumps through this list here, p goes through one after the other, feeds it to 2, raises 2 to that power, subtracts 1, gets a Mersenne prime. Now it's that triangular number. The mth triangular number that Euclid claims is also going to be a perfect number, which means if you sum its divisors, you're going to get the same number back out again. Well, let's test that. That's something to use generator technology in order to investigate. See if we get it, what he's even claiming. Before we can prove something, we at least have to know what it is. So the test is itself a generator, and every time I trigger a next method on the test, it's going to loop through a computation. And each time it's going to come up with the next bigger Mersenne prime. You can look these up in Sloan's online encyclopedia of integer sequences. It's a very well-known sequence. And here we are getting the 31st triangular number, finding its divisors, adding those up, and lo and behold, you get 496 back. So it is a perfect number. The sum of the divisors equal the number itself. There aren't that many perfect numbers. So we're getting some really major ones here, some really big ones. This is where you see why lazy evaluation was so important, because pretty soon we're going to get to the end of what a brute force algorithm wants to even try. And I'm pretty impressed actually with this processor, that it can use brute force to come out with this many divisors this quickly. But we do reach the end of it. Here we are. So we're still trying to loop around inside a generator, and we've gotten to the point where we're not going to get an answer in any reasonable amount of time, because this finding divisors algorithm is just a bare minimum brute force way of doing it. We're just counting up through the number. We break out at a certain point. We get 2 factors. Every time we find a no remainder situation, we've got the number we just used, and whatever it combines with. If it's unique, we add it to the list. And yeah, it's brute force, very, very, very simple. And yet it's enough to test Euclid's proposition, not prove. Um, and therefore Python's power is perfectly evident. I think this is a good demonstration of how you can plan your lessons for this kind of thinking.